Bismillahirrahmanirrahim. Today I'm going to present you a new lecture entitled Detection of Binary Signals in Gaussian Noise Maximum Likelihood Receiver Structure. Remembering our last lecture when we talked about baseband demonstration and detection, when referring to that block diagram in which we wrote that the decision making regarding the digital meaning of the signal can be developed by using the inequality H1, H2, H1, and we have here the threshold Z of t. This is static, the output signal. This is the inequality H1, hypothesis that S1 has been transmitted, the hypothesis H2 that S2 has been or was transmitted. So here we're talking about threshold. Here we are now going to develop an optimum threshold. We are going to develop optimum threshold by minimizing bit error probability, BB, which called bit error probability. So now we are going to write inequality relationship between conditional probability density function P Z S1 divided by P Z S2 inequality H1 hypothesis and H2 P S2 divided by P S1. Here we are talking about conditional probability density function which are called also the likelihood of S1 and likelihood of S2. Here the inequality H1, the hypothesis and H2. Here we have the a priori probability. So the optimum decision here, the optimum threshold, we have to decide that if this likelihood ratio PZS1 divided by ZS2 is more than we have chosen H1. In this case, we mean that S1 has been transmitted. If we choose likelihood S2, which means that PS1 has been transmitted. Now referring to the equation of the likelihood ratio of S1 will be equals to 1 divided by sigma naught root square 2 pi exponential minus 1 divided by 2 z minus a1 divided by sigma naught square. And also P conditional probability or likelihood of S2 will be equals to 1 divided by sigma naught root square 2 pi multiplied by exponential function minus 1 by 2 z minus a2 divided by sigma naught square bracket here. Now by plugging this, we will call equation number 1, this will be equation number 2, and this will be equation number 3. By plugging, substitute 2 and 3 in 1 by substitute 2 and 3 in 1 yields. So we have to clean the board because small board in this case. We will obtain the optimum threshold Z of t, the output Z of t, this static more than or equal to H1 H2 A1 plus A2 divided by 2, which will be equals to the optimum threshold level. This is called the optimum threshold. Optimum threshold level. Now we are going to obtain this optimum threshold level by minimizing the bit error probability. So we are going to draw now the two likelihood ratios for the first conditional probability and for the second conditional probability. This we are talking about the threshold gamma equals to gamma naught. The likelihood of S2, I'm going to draw now, and the likelihood of S1. Likelihood, this will be the likelihood S2 of t, likelihood S1 of t. Here will be A1, the signal components of S1. Here will be the signal components of A2 of S2. Here S2, here S1. Here we will have two types of errors. Once, if we transmitted the signal, S1 has been transmitted, and we have that the channel noise affects so that the output Z of t will be less than threshold. So first type of error, S1 was sent. We have channel noise, so that the output Z of t will be less than our threshold level. This is the first type of error. In this case will be extended. So if we are going to talk about the first error, P E S1 will be equals to P H2 S1, and this will be equals integration from minus infinity up to our threshold by PZ S1 dz. This is the first type of error. If we transmitted S1 of t, but we have here the noise, channel noise affect the output so that the output here will be less than threshold. So we have the tail here. In order to calculate later on, we will mention that the bit error probability in order to calculate will be the area under the tail of either sides of right or left. We're talking now about the first error. The first error, S1 was sent, channel noise affects so that the threshold will be less than, the output will be less than threshold. Second type of error, S2 was sent, S2 was transmitted, S2, second type of error, S2 was sent, but again, channel noise results in that Z of t will be greater than threshold. S2 has been transmitted, but we have here the channel noise affect that so that the output will be more than threshold. This is the area here, this place. So in this case, the second error will be called P E S2 will be equal to P, in this case H1 S2, and will be equals to the integration from the threshold, from our threshold up to infinity for PZ S2 dz. So we have two types of error. Number one, S1 was sent, the noise of the channel affect that, so the output will be here less than the threshold. So the calculation will be from minus infinity up to the threshold by the first likelihood of the S1 of t. Then the second type of error, if the S2 was sent, but we have again the channel noise effect so that the output will be more than the threshold. In this case, the error will be PH1 S2. Calculation will be from the threshold up to infinity for the S2 likelihood ratio. So in order to calculate the probability of error, which makes the optimum threshold, we have two ways. PB, bit error probability. In order to obtain the optimum threshold, we have to calculate, or from this to calculate from minus infinity, this function, the first one, to calculate integration from minus infinity up to our threshold for this case PZ S1 dz. Again, or will be the area under the tail of the other side. If we are talking about S2, will be equals to the integration from our threshold will be equals A1 plus A2 divided by our threshold by 2 up to infinity PZ S2 dz. The conditional probability. So in order to calculate the bit error probability or the error probability, we have to choose, it depends on what we have given, and at that time we can calculate from the integration from minus infinity up to the threshold for the first conditional probability likelihood, or from our threshold up to infinity for the second likelihood ratio. So in this case we tried to optimize the threshold by minimizing the bit error probability. This is the first criteria we are talking about. Next topic, we are going to optimize the receiver, the receiver, which we will call later on match filter, by maximizing the argument of complementary error functions. This is the first part of our lecture, talking about optimizing the threshold by minimizing the bit error probability. Our next lecture will be we will talk about how to optimize the receiver by maximizing the argument of complementary error function. Thank you. Enough today. See you next time.